Hello, everyone. Probably you must be wondering, okay, what is Titanic doing in a security conference? So I find some analogy between 5G and Titanic, so that's why I'm trying to, like, I mean, let's see what we can learn from Titanic. So that's my, purpose of putting Titanic here. So if you remember, I think everybody knows the backstory of Titanic, right? So it's been almost more than a century Titanic sank, and then it just when we speak of the design of the Titanic, so they they assume that because of the tight compartments, like on the bottom, so the ship wouldn't be sunk. I mean, it's unsinkable. But in reality, this was completely different. So when it hit the iceberg, so you see that the compartments are only like watertight in the horizontal level, but once it hit an iceberg, so the vertically, like once the hull broke, all the water actually entered in the first 6 compartments, and then from there, the ship started sinking. So having all the compartments like tightly sealed, like vertically, also horizontally, I think makes a big difference. And that's one of the design mistake that actually Titanic made. So same thing also appears in 5G as well. So what basically 5G network assumes is that there is a control plane, and then there is a data plane. Yeah. So, and then there is tight separation between control and data planes. And then there are some elements inside the control plane, like AMF, SMF. Then in the data plane, you see some elements like G node B, then user plane function. Um, I mean, for simplicity purpose, I'm not showing some of the elements inside the control plane. It's a complex architecture. So I'm showing like some key elements like AMF and then SMF that actually do your authentication. So as soon as you switch on your phone, traffic passes through the G node B, the base station, and then relay to the core network where authentication and encryption is performed. So that's how, like, I mean, end-to-end security between your phone and the control plane elements is set up. And then once that is set up, like control plane is done, like you're thoroughly secure, then opens the data plane or user plane. So from then onwards, like all the traffic can be encrypted from your phone, sent to the base station, gets decrypted, and sent to the user plane function. Like we see, it's nothing but like a router, right? It's like a forwarding element that's there. And then that routes your traffic to the internet, and then vice versa, the same activity happens. So the important thing here is like both these control and user plane are tightly separated. And if you ask me about security, well, of course, there is security. Like all the interfaces that you saw before, well, it's particularly like the over-the-air interface, there is NAS security, which, for example, like protects your control plane. Then there is RRC security. So there is all sorts of security also on the interfaces, like, and then the recommended one is using IPsec, so on the transport layer, right? But there is also one thing to understand here is that if these interfaces are physically secured, well, they are actually, then IPsec can be omitted from the implementation, right? So that's mostly you'll find networks or internal traffic is in plain text and not using IPsec. And then one essential thing you should also understand, like how the data moves across from your phone to the network. So from the phone, which is the UE, traffic like just like IP packets come to the G node B. G node B adds what we call a GTP header, right? And then you see the age of this protocol is like 26 years now, and like an age-old protocol still being used in 5G and probably also in 6G as well, right? The base station adds a header, GTPU header, and then forwards to the UPF, the router, and then forwards the packet outside, and then vice versa. So there is what we call this GTPU header, which is a very, very exploited protocol in telecommunications, and then still being used here, right? And in such a situation, because I mean, what I'm talking here is an attacker that is positioned from the smartphone, or like, I mean, not just smartphone, it could be any device that has 5G or cellular connectivity, right? So with a SIM card is able to send IP packets to the network. So that is the threat model that we are talking about. So it means everyone is an attacker in this case, right? So, and then we just need to know how to actually target control plane, data plane, and then know some things about it. So in such a situation, what we are talking is like, or the assumption of the network is there is a tight separation between control and data plane. What if attacker is able to tunnel or move the data from data plane to the control plane? Then begins like a big game. And then if the control plane and data plane are not tightly sealed, then there are two different kinds of attacks that that we can think of. One is like protocol tunneling. I think you might have heard this protocol tunneling term commonly in the internet as well. So SSH or your VPNs, like everyone use this protocol tunneling concept. So it's nothing like encapsulating one protocol inside another one so that the traffic can be routed to a specific destination. And then in this, in 5G, particularly like GTPU is an interesting target for protocol tunneling. Why? Because it's just doing simple forwarding. So inherently, or by design, there is no security for the protocol itself. And it doesn't verify the contents of whatever the payload of the protocol it is. So it becomes like much easier for an attacker to tunnel like packets inside this GTPU protocol, right? And then this is not a new, this is not like a new attack vector. So this has been exploited so many times, but not on 5G. And then like the GSMA, the carriers organization, already announced that such encapsulated packets are basically like fraud inside the network. So a tunnel packet actually looks like this. So you have an outer GTP header, which will be added by the base station, and then attacker creates this tunnel packet where he purposefully adds an inner GTP header, which is a GTP header that's added, plus a payload. I mean, payload can be any IP traffic or any other custom protocol that's understandable inside the core network, right? So for this packet, for this encapsulated packet, the attacker needs to specify certain destination IP addresses and ports, right? And then also a few other elements such as tunnel endpoint identifier. So if you are from the telecom world, I guess like you can easily relate to this terminology. But overall, these are nothing but like ports and then IP addresses, I think, which we all know how to obtain, right? So the difference between how a normal scenario looks like and then tunnel scenario looks like. So in a normal scenario, like IP packet goes, I mean, no GTP. So IP packet goes to G node B, and then the UPF removes the header and then sends the packet to the internet. So that's the normal flow. Then in the tunnel flow, the attacker is adding a GTPU header, and then G node B adds an extra header, which is very legitimate, and then sends to the UPF. Now UPS throws away the outer header and then processes the inner header. And if the destination is set to the UPF itself, so the UPF basically reroutes the packet to itself. So now we are talking about UPF that is again reprocessing another GTP header, which is actually crafted by the attacker. And then the payload, let's come to that. So the payload can be quite different things. And another interesting thing with 5G is it has an N9 interface, which connects two different carriers like home network and a visitor network. And if you're specifying an IP address somewhere that's located internationally, so the packet can be also tunneled to another international network as well. So we're not just talking about like domestic attacks, but could be also applied on a larger scale. Then the second type of attack, if both the planes are not tightly sealed, so this is what we call network boundary bridging. I'm sure you might have heard this in the regular traditional IT world as well. So this is like a packet from the data plane trying to reach one of the control plane elements. Yeah? Either that could be AMF or SMF. And in that case, like the payload should be either a protocol that's understandable by the AMF or as well as SMF. So there are traditional, I mean not traditional, but like custom protocols of telecom networks. So I wanted to try these things in field. Well, I told you just before that using encapsulated packets in the real world is actually like a fraud. So once it gets detected, probably like my research or everything could be like termed as fraud. So I was very careful in playing this. So I selected 6 core networks, and then thanks to the commercial ones, it gives more confidence, or somewhat interesting to also try them in commercial environments as well. So 4 of them open source and then 2 commercial networks. And then we set all of them into isolated lab environments. And then also no firewalls, like external firewalls, nothing like that, because I wanted to have like a fair evaluation among all of them. And then try all the different protocol tunneling attacks and then bridging attacks on them. And then I wanted to understand, by design is, what is the security? So, I mean, we don't want to add additional firewalls and stuff. So, I mean, that comes later anyway. So, and then in this, we also used a few SDRs, then a few 5G smartphones, then SIM cards, and then a few tools that will actually help us to create this encapsulated payloads, and in that, or encapsulated packets, and then have some custom payloads for them. Then some prior knowledge that we should have is IP addresses of these internal core network elements that could either be obtained via enumeration, or maybe Nmap could as well help us in that case. So what we found. Yeah, first thing, as I was expecting or anticipating that the net or the UPF processed the tunnel packet. So the UPFs, majority of the UPFs were actually processing the tunnel packets. Then that's the root cause. So once you process it, then you also execute the payload, whatever is attached to that, right? Then second one, the UPFs were also bridging the packets into the core, right? So, and then the essential thing the attacker should do here is to perfectly craft the packet so that it reaches the perfect destination. So there are two types of tunnel packets. One is that is targeting the UPF, and the other one is targeting the base station. So it could also, the UPF reads the inner packet and then again reroutes that back to the base station, not rerouting to itself, but then send it back to the base station. So this is another route that is open and available. A tunnel packet placed horizontally in Wireshark, vertically in Wireshark looks like this. There are 2 headers and then each pointing to a different IP address and also some ports that we are interested, right? Then boundary traversal, so the boundary bridging. So packets were sent from the UPF into the core network, either to the AMF or SMF, and there's a different effect when packets are processed by different network functions in the core, right? Now, for a packet to reach the AMF, the payload should be different. It should have an NG-AP protocol, right? Then to reach the SMF, it should have a different protocol, what we call PFCP, right? The one that's highlighted in the red is the actual payload that gets forwarded by the UPF into the core. Yeah. To actually achieve tunneling, or protocol tunneling and everything, but you also want to do certain kind of fraud. It's actually possible with these tunnel messages, but you want to attribute this fraud action to a specific target UV or a target mobile phone subscriber, right? So in that case, you want to learn what are the existing data sessions, or what are the existing handsets that are actually currently or connected to the network. So you want to enumerate with the same protocol tunneling technique to identify what are the internal identifiers, because I said there is something called tunnel endpoint identifier. So this is a identifier that's unique for everyone, and that's randomly generated for everyone for every kind of data packet that you're sending. So this is something internal. But an attacker with smartphone is able to extract that from the network, and there are few methods to do that. Use an IP address that could be either assigned or unassigned, then keep on mutating on what we call this tunnel endpoint identifiers. And then for packets that you receive back an error indication, which means the TEID doesn't exist, so it's free. Then if you don't receive a reply or an error indication, it means that there is an active session on that specific user, and then you have a valid identifier that you could use and then attribute the fraud to that specific user. So when we look at the UPF, the packet looks like this. It's tunneled GTP inside GTP, and then you have the actual payload there. And there is also another protocol in 5G that also helped, or maybe I think this protocol is actually new, got introduced in 5G, and this is basically replacing what we call GTP control plane, right? And then we also wanted to investigate how this protocol is implemented, then try different kinds of DOS scenarios, and then we see that some, or at least majority of the cores were actually crashing, because of certain undefined behavior in the specification. So we exploited that behavior where we send empty packets that actually causes crashes on some of the UPFs, right? And then we also do enumeration. Like TEID, there is another ID called session ID inside the network. Using a different type of payload, PFCP payload, we could as well enumerate the session IDs from the network. So now we have both of these IDs, and then we wanted to analyze how these boxes, the internal boxes, actually handle this identity management. How do they assign? How do they generate? If you look at multiple cores, we see that some of them don't even utilize the full 4 bytes for the identifier. They just use maybe 2 bytes, and the allocation is probably either sequential or maybe incremental. And then in some cases, it's random as well. So plus, when we keep on repeatedly enumerate, what we call is like rate, like there should be some like security feature like rate limiting, and that's as well missing in pretty much all of the cores. And depending on how the identity is managed, the speed of enumeration takes probably sometimes like seconds, sometimes hours, and sometimes like it's infinite. But as an attacker, like attacker is just looking for one TEID or one IP address that is actually valid. So like it doesn't take like infinite amount of time to get a hit for a specific valid identifier. So how do we use this in the real world? We did, putting all this together, like we are capable of doing a few attacks. We tried them on the infrastructure that we have. So first one is reflective injection. So you follow the packet, like the sequence number of the attack. So the packet originates from the attacker, a GTPU-style encapsulated packet, goes to the G node B from UPF, UPF reroutes it, and then this packet would be tunneled to a specific malicious server that's controlled by the attacker, and then on the response, it actually goes to not the attacker, but the response goes to the target UV. Imagine attacker initiates like a DNS query. The response would actually go to the target UV, like the victim, for example, or the TEID from that's actually forged or stolen from the network. Second one, having like direct route to the UV. So, normally direct host-to-host communication is actually not allowed inside mobile network, or else like all of us would have like free data like texting and everything. Usually packet leaves the core network and then again re-enters the core network, and then that's how you get billed or the like charged for whatever data that you're using. And in this case, like if you look at the sequence again, attacker injects a tunnel packet that goes to UPF and then gets rerouted to the base station and again directly to the target UV. So we just need to know what is the IP address of a specific target UV. Probably it should be in the same IP range that we are looking for. Another one is my favorite, like registering a legitimate let's say like a legitimate man in the middle. So attacker operates a false base station. Along with that, attacker has a handset that has a legit data connection with the network, right? And then it's very easy to lure phones to connect to false base station, and then all the traffic would now be routed from the false base station via the attacker control UV, and then in a legitimate connection to the base station, and from there to the network. So, and the protocols that we use, to be a bit more specific, so attacker just gets the NAS packets that are required from the victim UV, and then from there uses the standard a smartphone, and then whatever the data connection that's established, and then tunnel the GTPU packets, or the NAS packets are tunneled inside this GTPU to the core network, and then reverse back. So this becomes like easier for the attacker to finish like the control plane registration of any smartphone. So why? Because Once the packet reaches the UPF, it would be directed to the AMF, and we are talking about not using IPsec inside the network. So if the networks are actually not using IPsec inside the network, a rogue gnodeb can easily register as a legit one because you just need a few couple of association messages, and once you use that, a rogue gnodeb gets legitimately registered in the core network, and now we're not talking about like typical false base session attack. So we are talking something different, where the rogue gnodeb now receives the key material, like the cryptographic key material that's required to perform the encryption and integrity protection of all the communication from the UV. I mean, I just simplified this picture, just like it looks like the previous one, but the AMF will directly, as a part of a standard procedure, would send the ciphering or integrity protection keys to the base station. The base station now can provide like a legitimate service to the victim UV. And this is how the tunneling looks like, because we are tunneling standard 3GPP or like control plane traffic through GTP into the network and then getting back like in the same direction. So if you also observe, if you compare this with the real architecture or the general architecture that's there, there is no real route between UPF and AMF. I mean, never exists because there is no purpose or there's no procedure defined. But if there is a permissive routing rule, so UPF will forward whatever traffic or the payloads to the AMF and then vice versa. So in this case, what happens, like gnodeb receives the crypto and could provide legit data connection to the phone. And then you take like any of the security features in 5G, for example, authentication, encryption, like, or downgrade prevention, like none of them can actually detect such kind of an attack because this is happening because of some issues inside the network or because actually of processing the tunneled packets, right? And you take like Stingray detectors, or none of them can actually detect this kind of, or if you have like any other UV side security solutions, because for UV it looks like it's establishing like a legit connection with the perfect keys and everything. So yeah. So coming back to the root problem. So the root problem is actually because of processing the tunnel packets. And then GTP is a very efficient protocol for packet forwarding. Like, it's perfect. It has been used in 2G, 3G, and 4G and 5G as well. And what makes it inherently suitable for tunneling is because there is no built-in integrity checks or source authentication. So which means anybody can craft a header like this and then just inject it to the network. And I mean, let it be carried inside an IPsec, doesn't matter, because IPsec is only protecting your transport layer. So packet reaches the UPF, and if it gets processed, like, or if the encapsulated packets gets processed, then starts the attack. Then what's worrying is that modern UPFs, I mean, I don't care about 2G or 3G stuff, but what worries is like modern UPFs are also processing these kind of encapsulated packets. Having a firewall is entirely another story, but having these things fixed in the design, so probably, I mean, like what you can understand is that previous design practices are still reused in 5G, and I think this is something have to change, or something, I mean, vendors as well have to think about. I mean, there's no easy solution, this is for sure, because tunneling is already like well exploited over the roaming interfaces. If you look on the SS7 interfaces or GRX interfaces, encapsulated packets are always received, and maybe there is a prevention mechanism that side. But we also have to think about from the RAN side or from the radio side that anyone with a handset and a SIM card can also inject these packets into the core, right? Then we will see complex infrastructures in 5G networks. We're talking about slicing, and there'll be like numerous small private networks, and maybe they're not skilled enough to understand some kind of abnormal attacks that are prevailing in telecom networks. So probably some of you might have heard of GTP door. Yeah, like this is another. I mean, a backdoor that exploit GTP protocol to execute shell code inside the core network and then tunnel, like confidential information out of the network. So until some years ago, none of the firewall detected that. Now I think, there is some awareness in terms of detecting or identifying GTP door kind of attacks. Then same goes with encapsulated traffic. I mean, there can be multiple ways attacker can inject that into the network. So it's important. This should be prevented. And when I speak to some vendors, I mean, well, probably you might also heard the same answers, like there is not enough, like security budget on that, or maybe monitoring has to be done differently. So yeah, some recommendations and forward. So we disclosed it to all the open source developers and as well as the commercial ones. So at least some of them already fixed it, and I think we are still working with some of the vendors to fix them. And as well as there are some CVs in progress. So this research is already disclosed to GSMA. So we did it in one of their FSAG meetings. So they're happy to learn about this, and also a bit surprised to see why modern UPFs, modern core like 5G core networks are still affected with a vulnerability that was, like repeatedly told to be fixed in many documents and then so many places. So, but one of the thing that actually motivated me to do this is that because these protocols are something that are internal. Like, I mean, unless you are a pen tester hired by the vendor or the core network or like, let's say the provider, you won't get to know the operation of these protocols. Probably you can read them, like in thousands of pages and documents, but you don't get to know them, how they are built, how they are designed. So I started to investigate, let's expose this GTP protocol and then what exactly happens if protocol tunneling is, or if the network is affected with protocol tunneling and boundary bridging. And then you saw the kind of attacks, they become like super sophisticated. You don't need, complex RF attacks, nothing, just a simple tunnel packet to get legit encryption keys out of the network and then provide service to the UV, right? Yeah, some ways to fix this. Well, we always want to fix where is the root cause. Like, I know, like, if you go into the marketplace, there are hundreds of companies that are trying to sell you firewalls that, may or may not prevent these attacks. But it's important to understand that UPF is like a heart of the data plane, and then data is what, like, precious in 5G networks. So, and imagine how many number of devices that are, or maybe how many organizations that are willing to connect to 5G networks. So, I mean, as an example, I picked like smartphone, but it doesn't have to be smartphone. Like, it could be an industry, automotive devices. So, yeah, you name it. Right, some takeaways. So, modern UPFs, they are still vulnerable to encapsulated GTPU packets, and then it actually opens door to protocol tunneling and then bridging attacks. And this has already been recognized by Mitre in their threat modeling. So it's important to investigate or like also look around how these attacks can be done in their infrastructure, like by themselves, for example. So we also see like insecure practices. Of course, they are not the actual causes of the attack, but not having like randomized allocation of identifiers. And I mean, we are in 2025, and then these algorithms should have been already optimized or like secure enough so that we're also talking about like rate limiting. So all these like basic features should become like mandatory in any kind of design, let's say. We tested on 6 of them, 6 different 5G core networks. And more than like 80% of them are affected. Then also includes like commercial ones as well. So the kind of attacks that we see is they become like more powerful attacks and then undetectable on like also on the core, also on the subscribers as well, and will lead to billing fraud as well as like a legitimate man in the middle. That's I think that's the worst thing that anyone would want to have, right? Then there are also like insufficient guidelines on like the UPF design practices that I saw, because there is only the statement that, you have to just eliminate encapsulated packets. So that's the only statement you see. but there is no in-depth understanding of, okay, why this packet should be eliminated, and then what is the effect of it. So we did this into a full research, and then this will be published this October in ACM CCS. So if you would like to get more in-depth understanding of the exact methodology and everything, feel free to check out in October again. Right. So coming back to the analogy, like why I chose Titanic. So basically, the Titanic compartments are this 5G isolated trust boundaries, like control plane and user plane, or you talk about like network slices and the interfaces. Then iceberg would be the attacker with a smartphone trying to generate or push malicious traffic into the network. Then the water flowing over the boundaries is the protocol tunneling, because it's missed. I mean, these kind of attacks are missed or not caught by the network components. So they will let attacker propagate from one plane to another plane. Then there is also like an overconfidence in the architecture of the Titanic. So they said it's not unsyncable, but when the danger happens in a specific way, maybe it could be a corner case, So then there is a misplaced trust in, like also in 5G isolation. So the belief is that user packets never enters control plane. So there could be some kind of like relaxed environment inside the core network, like not using IPsec, for example. So it's not a good strategy. So having overconfidence, definitely no. And I hope you enjoyed the talk. And if you have any questions, I think we still have some time. So thank you.
Hi, one short question. You're familiar with the 5G security guide from GSMA? Because it stated that GPU traffic needs always be encrypted with IPsec, even end-to-end from SIM card up through the EPC.
Right. Yeah, I mean, it can be encrypted. I mean, there is a protocol to encrypt it. So, but the question is like, what is happening inside? I think neither I can see nor you could as well see what it is in implementation. So
end-to-end encrypted with IPsec, so you cannot tunnel anything.
No. End-to-end I encrypted between the G node B and the UPF, right? So it's only that.
Handset.
I mean, probably. I mean, handset is not using IPsec. It could be like whatever.
Handset has in the SIM card the certificate.
No, I mean, let's say, like, how does your WhatsApp traffic go? Like, is it using IPsec? Probably it has TLS, right?
No.
No?
IPsec. You have G node B.
Mm-hmm.
G node B speaks. G node B cannot look into the traffic, cannot look into the.
It's okay, a bit.
Because it's transparent encrypted. And on your subscriber module, you have the certificate to build the IPsec tunnel for the payload.
So. Actually, I mentioned one thing. I mean, even if you're using IPsec, the tunneling still works because IPsec is not protecting, I mean, it's not verifying what is there in the application level. So this is a packet that's coming from your apps level. And then IPsec, I mean, I'm happy if there is IPsec, which is fine. But once the packet reaches the UPF, IPsec is dropped. Yeah, we don't need it. And then the actual problem is like how UPF handles this crafted packet. So there are some UPFs that are actually processing these crafted packets. Then there starts the problem. Yeah. So that's an implementation problem. Yeah. So, and then which is found in many UPFs.
Hi. So I think maybe I missed it. What's the legitimate use of GTPU?
So that's the standard protocol to carry traffic from G node B to UPF. So whatever IP packet that you're sending from your phone reaches the G node B, and then GTPU header gets added to that, and then would be sent to the UPF. And then UPF decapsulates that the same in the reverse direction as well.
Okay. I guess I just don't understand why that has to be encapsulated.
No, I didn't get you.
I don't understand why that would have to be encapsulated.
Okay, so I mean, you're on the air interface. I mean, there are like thousands of UEs here, like sending data to the network, G node B, and G node B and the UPF basically establishes like a tunnel for you. Like we call it tunnel inside.
Oh,
like
okay. Now I get it. I got it. Okay.
And then that should be identified with you'll be identified with an identifier there.
Right. So. Got it. Okay. Now I see. So when you were doing your testing, you actually had to simulate both the user plane and the control plane?
Yeah, yeah,
Got
we
it.
had both of them.
Okay, got it. Thanks.
I mean, if no further questions, then, yep, thank you.